Bien, bonjour à toutes et à tous. Donc aujourd'hui, nous avons le plaisir d'accueillir Quentin Cazères. Non, Cazères, pardon.
Cazères.
Cazères.
Tu m'as demandé il y a 2
Pardon.
minutes.
Nous avons le plaisir d'accueillir Quentin, qui est à terre ici. Quentin a fait sa thèse donc, au Cerfax. Et donc après, il nous a fait deux années de postdoc à Cambridge. Et donc là, actuellement, comme je disais, il est à TER. Et il va nous expliquer des choses sur la simulation numérique de la combustion. Allez, à toi, Quentin.
Merci. Est-ce qu'il y a des gens qui veulent que je fasse la présentation en anglais? Okay, so English it is. So, what I'm going to talk about today is, are we doing numerical simulation of combustion right? So, basically, I'll be talking about biases of doing numerical simulation. So first, what is combustion? It's fairly simple. We have a fuel, and it's going to react with an oxidizer. Through a global reaction, it will give us products, mainly CO2, H2O, and we have the nitrogen coming from the oxidizer that remains there. For it to be properly combustion, we have to give up heat because it's an exothermal reaction. We can have parameters in the reactants. It's going there on its own. So what we have here, we can define what is called an equivalence ratio, which is basically the amount of fuel we have in the reactants and a molar stoichiometric ratio that will give us the stoichiometric proportions of how much oxidizer we need to get what is commonly called full combustion, so giving CO2 and H2O. The problem is, this is actually not chemistry. That's just atomic balance. So that's not the reality of what we have. In real life, if we take this again, the fuel, which is here the general formula for hydrocarbon, can be many things. It can be hydrogen, methane, butane, but also blends of any of those. Kerosene, which is hundreds of different species with a variation from batch to batch. It can also be fuels that do not have only carbon and hydrogen in the structure. It can be oxygen, it can be chlorine, a lot of things. And also it can be diluted. And also all the complexity that this fuel can be different depending on where we are in a mixture. Then the products. It's not only CO2, H2O, otherwise it would be a bit too easy. We have also carbon monoxide, which is harmful. We have what is called NOx, so nitrous oxides. They are poisonous. It's mainly it's small particles that can go into your lungs. It's also involved into acid rains. You have soot and many other species. Then this part, global reaction. It's not a straight path from reactant to products. Here is the simplest way of picturing going from methane with oxygen to CO and CO2. And this is a simplified version of it, okay? So all the arrows are what we call elementary reactions, and the whole set of elementary reactions that is describing the combustion is called a detailed kinetic mechanism, and that is done by chemists. Such labs are, for example, in Politecnico di Milano. We have other labs in France and all over the world. They are properly chemists. We are fluid numericists. So, just so you know, combustion is a highly nonlinear and multiphysics problem. Now, we want to know, why do we study combustion? The reason is this, the warming stripes. If you're not familiar with what it is, this is the variation of the global temperature for every year since, I think, 1950, maybe. And we are in the dark red, so global warming. And global warming is mainly due to greenhouse gases. You've seen at the end in the products that we had CO2, and CO2 is a major one. And most of the CO2 emissions, I mean, all the CO2 emissions that we have are basically due to combustion. A very huge part from coal, oil, gas, and then we have cement, flaring, and other kind of industries. And what is the use of that combustion? We have mainly electricity and heat that has kept increasing over the years. This is greenhouse gas emissions, not only CO2. So you see that you have approximately 15 billion that is not CO2, but still huge portion is CO2. So we have electricity and heat, transport, manufacturing, and a lot of other topics. Okay, so we want to study combustion to study how we are going to emit greenhouse gases. So what are the solutions to global warming that are presented by politics and industry? We have first family, which is carbon-free fuels, so fuels that do not have any carbon in the molecular structure. We have dihydrogen, ammonia, and metals. So no carbon means no CO2 at the end. We have biofuels, so they come from biomass. They include carbon, but the idea is that because it comes from plants that absorb CO2, you absorb CO2, you release CO2 by burning it, so you should have a net zero emission. And the other one is efficiency, because if you have more efficient engines, for example, you need less fuel, so you automatically do less emissions. Okay? So, sounds great, but there is a tiny thing to consider. Second law of thermodynamics. This is the mathematical expression. And if you want to say it in a non-scientific way, to get energy, you need even more energy. That's basically what it says. So, in a world that is subject to infinite economic growth, the energy consumption will increase. So if we increase the energy consumption, basically it means we increase the usage of natural resources to produce energy. So there are people that are questioning the infinite economic growth, and basically what they have to say is that maybe just changing the fuels is not sufficient. What we need is to stay inside a donut. So we have the social foundation under which we should not go. So this is life satisfaction, health, nutrition, and all the basic human needs. We should not go under that. And there is the ecological ceiling that we should not go through. And this is the G20 countries, and you see that ecological ceiling, we are above on everything. So it's not only about diminishing CO2 emissions, it's also about diminishing every other thing. So for biofuels, for example, we can diminish the CO2 emissions by using biofuels, but then we might increase ecological footprints. For hydrogen, we might, if it's produced from water, we might go into this part. So it's about the whole conception of ecology and not only CO2 emissions. Also about new technologies, there is a paper from the University of Cambridge called Technology to the Rescue. Basically, it's studying if the net zero strategy in the UK is efficient or not, and if it will help in decarbonization of the world. And this is what it says. This is the conclusion of the paper. Basically says the techno-optimistic approach to mitigation depends on two technologies: zero carbon fuels, the one we are interested in, and carbon capture technology. Neither has materialized at scale to date, yet play substantial role within decarbonization pathways. So we are relying on things that are not ready. A review of the energy literature and modeling of historical deployment rates show that the arrival at scale is increasingly unlikely. So why am I saying that? Studying combustion and alternative fuels, that's fun, and we should do it. Say that this is the best way to decarbonization? No, maybe not. First step, decrease our energy consumption, and then, only then, we can say that carbon-free and alternative fuels will be useful to fight against climate change. So that was the context, and it was important to say it for the whole context. Now, let's science. We saw why we study combustion. Let's see how. We have two main regimes, which is premixed combustion, in which we have the fuel and oxidizer mixed together and then it burns. So we have here the mass fraction of a few molecules and the temperature that is rising. So you have them together and then it burns. And we have the non-premixed combustion, in which we have the methane coming from that side, so the fuel here with a mass fraction of 1, and the oxidizer coming from the other side, and it burns in the middle. So that's why the temperature here is a peak and not something that increases. Okay? This is canonical, so reality is in between, especially when you have turbulence that is doing some mixing. So you might inject things in a non-premixed way, but then it will mix. So it will burn in something that is kind of in between. There is one concept that is important, is the concept of equivalence ratio. It's so basic that it's on page 12 of the Thermal Numerical Combustion book that we call the Bible in the field of numerical combustion. And this is how it's defined. So this is the equation from the beginning. And the global equivalence ratio is the amount of fuel in mole over the amount of oxidizer that we have in this mixture, compared to the amount to reach stoichiometry. So stoichiometry is what we have over there. So all the carbon goes into the CO2 and all the hydrogen goes into the water. And this is, this thing here is Sx, okay? So why am I talking about this? It's because for premixed flames, it's a very important quantity. If we look at the laminar flame speed, so this is the speed at which a planar flame propagates, we see that there is a very huge variation with the equivalence ratio. So it's important for the dynamics, but it's also important for the pollutant emissions. Here that's nitrous oxide, and we see that we have nothing in what we call the lean part, so below 1. We have first peak at 1 and then another peak in the what we call the rich part. Okay. From this we can also do some chemistry, some local chemical balance. So counting the amount of mole of an element. Elements are carbon, hydrogen, nitrogen, oxygen, the atoms. Okay. So this is how we count that. So just sum over all the species K in which you can find the elements. And if we do that, stoichiometry says that we have the number of oxygen atoms is 2 times the number of dioxygen molecules. this is equal to twice number of carbon plus 1/4 of the number of hydrogen, and this sum is 0. And we can say that, so this is a stoichiometry, and anywhere else we can say that it's a value beta. Then what we can do is define a local occurrence ratio. So to do that, we use the value of beta that we can compute like this. This is the mass fraction over the molecular weight. And when we normalize that, we can first have what is called the mixture fraction. So this is a value that is 0 in the oxidizer and 1 in the fuel. So you can see the amount of mixing you have. And if you put that with the stoichiometric value, you can find again the occurrence ratio. So this is the way that has been used to find what locally the mixture is. There have been other definitions that are not relying on the mixture fraction, but are also local, depending on the number of atoms that you have. And there is one big difference with those, that they do not have references. In this, you have the value in the oxidizer and the value in the fuel. So if you remember what I said, sometimes you don't know what is the oxidizer and you don't know what is the fuel because it changes over time. So this is a problem. So there have been some other definitions, and they are more accurate for a chemical point of view, and I'm going to show you why it's better. So this is the laminar flame speed for 4 different fuels. You have methane and ethane, CH4, C2H6, and methanol and ethanol, which are basically the equivalent with an oxygen atom in the composition. So what you can see is that methane and ethane, orange and red, are pretty similar. Ethane is higher, but overall same. Methanol and ethanol go way further in the rich part. Okay? And this is weird because it shouldn't, it can be like that, but also if you use another definition, which is the one based on oxygen that doesn't have reference, everything collapses on this side, which is better for comparison. It's easier to compare something that has the same shape over the whole range rather than something that goes further away. And it's not about looks only. If you look at the gradients of the methanol laminar flame speed, basically you see that the first definition does quite a bad job at representing the variation, because you have this part of the gradients that is not changing. So it's basically saying that it doesn't represent anything in this part. If you change the definition, you have something that is more meaningful and that can be used in a more compact way. So all the other definitions basically they lacked generality, so there was a need to make it more generic, and for that you define a reducing and oxidizing propensity. So it's basically how much electron can be given by an element, that's the reducing propensity, and how much element can be received by the element, oxidizing propensity. This is not perfectly chemically accurate because you have ionizing and covalent bonds, but this is the general idea. We don't really care about that at that level. And you say that the general propensity is just the sum of all the elemental propensities. And you can put them in a table, and you see that you can define one for exotic atoms. Like you have aluminum, sodium, phosphorus, and in the oxidizers you can have fluorine, chlorine. It all works for the same, in the same framework. And you just do the same principle as before. You compare reducing over oxidizing, and you compare it with the stoichiometric value. But by definition, this stoichiometric value is 1. So overall, you have a very simple definition that works for everything. Okay? Okay, I'm gonna skip this part. It's a bit too technical. This definition doesn't only work for gaseous mixtures. Here, for example, we have heptane droplets that is evaporating into a mixture of hydrogen air. And you can define an equivalence ratio between the gas phase and the gas phase, and an equivalence ratio between the liquid phase and the gas phase, and then a total one. Psi here is for the different phases, and it's a bit more tricky in terms of counting the amount of elements that you have, because you have to count them in a control volume, but it basically is the same. And what you can do is define an overall quantity that's just reducing propensity in the solid plus the one in the liquid plus the one in the gas, and same for the oxidizing propensity. There is a minus over there. So here, very easy, sorry, you have the total equivalence ratio that is just the sum of the one in the liquid and the one in the gas. So this is just definition that can be virtually applied to any system with an infinite number of phases with any composition. So very useful if you want to compare stuff, because basically you can compare all the mixtures you want in the same, within the same framework. And it doesn't care about if you have preferential diffusion, preferential evaporation, or any homogeneity, or because you don't need to assume what is the fuel, what is the oxidizer. It's just about atoms. There is another concept that is relying on this, is the bonding fraction. If you look at this, this is a diffusion flame, like I presented earlier. In this diffusion flame, so I have one for hydrogen, methane, ethanol, butane, and dodecane. Okay, and if you put them in space, the mixture fraction space, the one that is very useful because it goes from 0 to 1. The problem is, because of how it is done with reference values of the oxidizer and the fuel, you can see that they have a similar shape, but they are actually not in the same space because the normalization is different for each. This doesn't change, but beta F changes for each fuel. So basically this is a mess. You cannot really compare anything like this. And this is one of the most used variable for modeling in the field. So the easy way is to make something new, and you just get the propensities again, but you kind of normalize them. So you just add the reducing propensity at the denominator. And what it does is that everything collapses nicely. And also what is nice is that ethanol, that was in green over there, and that was kind of a rogue compared to the other ones. It also collapses with the rest, even though it has an oxygen atom in its composition. And you can see that the secondary peaks that you have over there, this is heat release rate, sorry. the secondary peaks, you may think, okay, maybe they collapse, but you cannot be sure looking at this. But in that framework, you are sure that they collapse. So this is important in order to have the ability to compare different fuels in the same space. And that's something that was not really done before. But now that we are doing stuff that is more complex, we need that kind of framework. So this is a paper that was recently accepted called Unifying Definition of the Local Equivalence Ratio for Complex Mixtures. And the aim of the paper is just to provide a framework to the community, and all the correlations and things that have been done in the past, maybe try this concepts on the existing theory and see if we can find things that are a bit more generic. Because we do more complex mixtures and systems, we need things that make sense. In terms of modeling, so I'm gonna skip the details quickly, but basically we do not always compute all the species in a combustion system. Sometimes we do CFD, we transport, and instead of transporting species, we transport the mixture fraction, the one I presented before, because it behaves at a passive scalar, so it's very easy to have it in a convection diffusion equation. And in one of the combustion modeling, one of the ways of modeling combustion is that you create a map giving the scalar dissipation rate of a variable called the progress variable, which is basically 0 in the reactants and 1 in the products. So it's something that tells you how advanced the whole process of combustion is. Okay? And we had a case in which we have a spray of heptane, and the oxidizer is just not air, it's methane blended in air. And the amount of methane you have in this air can vary. So you have several equivalence ratios for just the oxidizer. And if you do a map of this quantity in the mixture fraction and progress variable space, this is what you get. So you do a lot of different laminar simulations, and it gives you something that will be included in statistics. And you can see that the maps are fairly similar, but the values for the stoichiometry because the oxidizer is changing is different. And you have the peak value over there. So we said, okay, let's see what it does if we superimpose everything. So if you do 50 different oxidizer compositions, you have this. And this is an absolute mess. You cannot do anything with that kind of map. But if you put it in bonding fraction space, everything collapses really, really nicely, like surprisingly nicely. So you have 50 points over there, and they all collapse to a single point. So it kind of means that even though the oxidizer composition changes, if you put everything in a space that makes sense, they all behave in a similar manner. And what you can do is just interpolate everything and make a single unique map, and you have one map that can do 50 different compositions. So this is very useful for modeling, and this is a work that we are starting exploring this for modeling with a colleague at IMFT. Okay, now we know how it mixes. Now let's study how it burns. To go quickly, in CFD, you transport 5 equations mass, momentum for each component of velocity and energy. And if you do reacting flows, you also transport one more equation per species. This is okay if you're doing hydrogen because you have 12 species involved in hydrogen combustion. It becomes to be tricky if you look at methane, especially if you want to look at emissions. And if you want to look at biofuels, biodiesel, for example, you have 3,300 species. So we are not solving that in a CFD code. No CFD code is able to solve this, especially on a 3D case. Okay, so go fast on that. Basically, what we do is that we reduce the chemistry, and we have several methods. And the one we chose is this one. So mathematical techniques to discard unimportant species and reactions, and that doesn't require optimization. So just having the full graph of the interactions between species and do some pruning. Look at the data from laminar calculations that are really quick and see what is useless, what is important. These are all the techniques, but I go fast on that. So how does it work? We take a set of canonical cases, representative of the bigger case. So if you have an engine, for example, that works at 10 bars with an inlet at 1000 Kelvin or 700 Kelvin, you choose those conditions and you do 0D reactors, so really fast computation, or one-dimensional premix laminar flames with a lot of assumptions, but that are fairly representative of the combustion process. You do this, you select a target. So target is basically a quantity on which you want to evaluate the sensitivity. So what we are interested in combustion is heat release rate, because that's what gave the rise of temperature. But it can also be methane, pollutants, carbon monoxide, and a lot of other stuff. Do this. And finally, what you say is you need error thresholds. So you're taking something that is accurate and you want to reduce it. So of course you will make errors. This is how it works. But you can say, okay, I want at a maximum 5% error on the time that it takes to ignite, or the laminar flame speed, or the final temperature, or the amount of nitrous oxide that is produced. So this is the whole general framework. And this is what it looks like. So A, B, C, D are different species. This is the target. And basically you rank the species in importance for the data you have, and you remove iteratively. So here, let's say, so you multiply the contributions to A. Here C has a really low contribution. So we say, okay, we remove species C. We recompute our case, see how much error we have. If it's good, we keep going. If it's bad, we stop. And we might do something else. We might employ another strategy. This is complicated, but it's all done automatically in a code that I developed during my my PhD. And it's relying on a chemistry solver, and it's basically you just give the input I showed, and everything else is done automatically. So very easy to do. And this can be applied to hydrogen, methane, the blends. So all the fuels that I've presented. Other stuff that is burning or degrading thermally. So it's been used for batteries, fire, because you have a lot of different species in the battery, and when it catches fire, you want to know the dynamic of that fire. Also thermal decomposition of sarin gas, because it could be interesting to know if you heat up some sarin gas if it actually remains toxic or not. But it's also used in biochemical processes. So not only stuff that burns, because it's been used on something that is called a coagulation cascade. So basically how blood coagulates, and that's not burning, hopefully. So same methodologies that were applied to that. And this is actually a paper we did with Juni Chen in Montpellier, and it showed really good results. So basically, if you have a graph that needs to be pruned, I'd be happy to help and just try methodologies from combustion on other cases. Okay, so now let's do some CFD. I'm going to show you a case of hydrogen-enriched methane air flames. So it's basically this configuration. You have a mixture coming from the bottom, going through a swirler and attaching to a bluff body over there. And this is the chamber in which you will have the combustion. So what you need to know is that you have two cases. One in which you have the fuel is composed of 60% of hydrogen in volume. The other one is 90% of hydrogen in volume. So what are we interested in? We want to know the heat release rate of a flame. That's one of the main quantity we want before looking at pollutants. The problem is, via experiments, this quantity is not accessible. You cannot directly measure heat release rate in a flame. So what is done in experiment is that you measure the emissions of the excited OH radical. So basically, when you burn, combustion will create what we name OH star, which is the excited state of OH. And when it de-excites, it will release a photon, and you can see the light emitted by that. And what you see is that for the 60% hydrogen case, we have a V flame. And so this is just half, so it should be a V. And for the 90% case, we have what we call the NEM-shaped flame. So very different dynamic. And just so you're convinced, this is the correlation between the position of the peak value of OH star and heat release rate. So you can see that it's a decent assumption to say that OH star equals heat release rate. So we did the computation with a fully compressible LES solver called AVP. A lot of technical details, maybe I'm not interested in that. We had measurements of temperatures on the walls of the burner, so we can impose the temperature at the walls. So we also have heat losses. It's not the best way to do it, but it's reasonable for that. So what we do is that we try to validate the cold flow first before igniting it. And we concluded that it had a good agreement. But I'm not that much convinced by good agreement, because obviously we're wrong in some cases. And I'm not alone. If you look at what you have in the community, in a lot of cases, most of the flow is accurately produced, even though you have some errors. LES show good agreement with the experiment, even though you also have errors. And that's not really satisfactory. We should do better. And basically, numericists blame the experiment for being wrong, and experimentalists blame the numerics for being wrong. So we'll come back to that. If we look at the results, if we look at the heat release rates, we can see that 90% case, we're good. We have the M-shaped flame. This is the height of the flame. For the 60% case, we have kind of an M-shaped flame. So we do not have the V shape that we were supposed to get. So we are wrong. Except that if we look at the 60% case with OH mass fraction, so directly the species that is emitting photons, it seems good. So in this case, we have the heat release rates that doesn't really correlate with the OH star emission. So our basic assumption of how to compare experiment with simulation doesn't really work. So we need to work on that. This can be due to the fact that the actual enrichments changes over time. So in white, you have the normal value of enrichment, so 60% in that case, 90% in that case. But you see that there are some variations. This is because the hydrogen diffuses faster than other species. Now we are going to look at liquid fuels. The specificity of most liquid fuels, if you look at kerosene, for example, is that the composition is absolutely not easy. This is the actual composition of the kerosene that is used in every aircraft. So it's regrouped into families, N-alkanes, cycloalkanes, aromatics, and this is the number of carbons that you have in each family. So you have hundreds of species, basically. So what we need to do is make an assumption. Say, okay, that's just actually 3 species. And that's what we can compute. If we do that and we do a reduction, we end up with a mechanism that instead of having more than 300 species has roughly 50. We put that in pseudo 1D domain. So this is just a channel, basically, in which you have burn gases over there and a droplet that we inject just before the flame front. So basically all the fuel is coming from the liquid droplets. It evaporates and feeds the flame front. Once we do that, we can look at the temperature. So it's burning, temperature is rising. The mass of each of the molecules in the droplets. So you can see that at the end, droplet is fully evaporated. And then you can look at the heat release rates with the consumption rates of each species. And you can see that they are not burning altogether. This is stage. So you have the most volatile species in yellow that is consumed first and actually evaporating first, then xylene in green, and the most present species, dodecane, that is consumed over a long period of time. That's why you have this trailing heat release rate. So it's just not one peak, it actually continues for longer. And you can see this if you look at comparison between the evaporation rates and the consumption rate. So here it evaporates really quickly before the flame front is consumed. This one is basically evaporating and being consumed at the same time at the flame front. And this species evaporates after the main flame front and feeds the trailing heat release rates that we saw earlier. Okay, so I'm going to wrap up. We need to do better because in that case, there is a tiny problem. We reduce the chemistry on a gaseous case, but how do we know that it works for this case of spray combustion? and we need to adjust that. So we want to do better by coming back to fundamentals. First, the code flow comparison that I showed you before. Good agreement is not enough. We've been doing LES for a long time. Maybe we should be able to do better. So the idea is to perform a simulation of an experiment, but introduce tracers or oil droplets and perform PIV, particularly induced ferrosymmetry, on that. So just reproduce exactly the experiments to be able to see what's wrong. If it's the experiment, if it's the numerics, we need to know. So there are a few challenges because we need information about the seeding, about how the laser sheet will interact with the particles, so some optics as well. And this is a project that I started with a colleague of mine, Preeti Sandarajan, in the University of Southampton. That will help us know what is wrong with our cold flows. Then we have something else about the chemiluminescence, so emissions of photons and radicals. So we have another configuration called a jet cross flow. So you have air over there and hydrogen. And here you can see a flame that is red at the tail. So this mainly comes from water molecules. And then you have blue. But blue is usually associated with CH star. And hydrogen doesn't have carbon in its composition. So it's weird. Some people argue that it comes from H2, a reaction involving H2O2, but we don't really know. So the idea is, again, to reproduce the experiments, including the chemistry, to know what it is about. And this will be done in collaboration with the same colleague. And finally, for liquid fuel chemistry, so if we take the same configuration with a droplet of heptane, we use the full detailed kinetics, the one with over 500 species, and we reduce one on gaseous cases, but with a really, really tiny error on combustion. We look at the results, and it's actually different. So what we have, if you look at the mass source term, according to the detailed kinetics, the droplet should evaporate way faster. And that's what you have here. The peak of heat release rate is shifted. So yeah, there is a kinetic effect to that case, because it's exactly the same case. The only thing that changes is the description of the chemistry. So there is something wrong. We need to investigate that, and this is a work that will be presented at a conference in Edinburgh in April. Still a work in progress, but we see that reducing on gaseous flames doesn't seem to be enough. So, to conclude, there are plenty of things we can do in combustion, in numerical simulation, but we also need to ask ourselves if we are analyzing them correctly and if we are doing the right things. So for this, we need unified definitions that will allow us to compare things that look different. Remove biases and have assumption-free digital twins. So really simulate what is actually done in the experiments and not assume that something is going to correlate with something else. And do more fundamental work. So really going to the core, okay, gas kinetics, is it really similar to spray kinetics? That concludes it. I want to thank you for your attention and thank all my collaborators in the different labs I've been to, and also thank the collaborators in the making. And it could be you. Thank you.
Thank you. Merci. Questions or questions in the audience?
Merci, thank you for the presentation. I'll try to have a French accent in my English so that it's maybe better.
No problem. You can do
Okay.
whatever you want.
For the presentation, we've been burning things for millennials from so many time, but we still don't understand how does it work.
Yeah.
So this is the main message. I wanted to ask you, in the case that you showed in slide 50, for example.
Yeah.
With the droplet of
Yeah.
kerosene-like Jet A1
Yeah.
system, that one, yes. So if I understand well, it boils down, it behaves like a premixed flame.
Yes. In
Okay.
that case, yes. But let's say different premix flames. So it's mainly like a premix flame. That's what we want, at least, with a spray flame. We want it to evaporate early enough so that it behaves like this. But this is a bit tricky.
Okay, because you got the temperature that is monotonic.
Yeah, of course. It's because, so actually what you have is that these two make it behave like a premix flame, because basically they evaporate before, so locally you have premix mixture. But this one, it's a bit more complicated, because basically it's gonna evaporate in the burn gases, so it goes both way, basically. So you have towards this side, it behaves like a premix flame. Toward this side, you can maybe say that it behaves like a diffusion flame, because the oxidizer feed and the fuel feed will be opposed. So it's kind of the part where premixed and non-premixed doesn't work anymore. Yeah, sure.
Thanks for the really nice presentation. So first, let me come back to what you call the Bilger's formulation.
Yeah.
I think so. I know that Bob is dead now, but I think you should first mention Schwab and Zeldovich for that.
Yeah.
Okay.
Yeah, sure.
This is historically.
Yeah. That was just to
to
be quicker.
For the history of combustion.
Yeah.
And so now I have a question. So I would like to know if you look at you show how you collapse the laminar flame speed with your formulation, which is really nice. But so then I am wondering. So you know that there are a lot of investigation right now on what you have on the left, because this is where you need a smaller amount of fuel, right?
Yeah.
And so you have a turning point, right? When on the left and on the right also.
Yeah.
Also, and these this investigation were led by Vincent Chauvin-Gigli in the 80s, right? So did you look at what you can find as a turning point here? Because this is
Not
the
really.
flammability limit, right?
Yeah, I did not look at this exactly, but I looked at something else, which is, so I skipped this for clarity, but basically the table over there, all the values that I gave in the table, they are just generic values. For example, for carbon, it's saying that one atom of carbon will react with 1/2 of an oxygen, because you have two possibilities of bonds in an oxygen to give CO2. But in combustion, you actually do not produce only CO2, you also produce CO. And this is what it looks like. So CO, if you do the same exercise, it has a reducing propensity of 2. And this is how, so this is not really equivalence ratio, because otherwise it's a snake biting his own tail. So this is the number of carbon divided by the number of oxygens in your mixture. If you do that, you can see that at the beginning you have almost all CO2 and then CO, and then it changes. And you can have a variable reducing propensity for carbon that starts here, which is actually not 4, because the amount of carbon, even at really lean mixtures, is not actually 1. Some of the carbon goes into other species. So you can have a variable one. And if you do this, it kind of changes the laminar flame speed, how it's represented. So instead of having the peak value that is slightly above 1, you actually put it right before 1. So this is another view of, this is exactly the same framework. So it's very easy to change, and in a paper it's not about, in a paper you just have to say, I'm using that reducing propensity, that value. But it means that depending on actually what you consider being the stoichiometry, if it's the ideal stoichiometry with only a single product, or if it's a mixture that shows the reality, maybe you can change the way this curve looks. So maybe that could be a way, like take that framework and see if there is something special about this turning point, and maybe that the products change, and maybe what we call stoichiometry in that case, maybe it would be a bit different. That would be the approach, but no, I haven't looked at it. But it could be interesting.
As I mentioned, I got other questions on slide 50.
You like this one?
So actually it's a double question. The first one, do you have any experimental evidence of what you say here is true or not?
No, that's
Okay.
that's the problem, because what I'm looking at are things that you cannot quantify,
You cannot
experiments.
quantify.
because
but-
it's hit release rates
No.
not accessible.
So do you have any clue? So you mentioned that depending on the model that you're employing, you could have different results. So
Yeah.
you have a dependency on the heat release of each species that you got here and there. But so this is, of course, so this is about, and that's a very good point. But on the other hand, you could have a dependency as well on the numerical method that you employ over there.
This
Because
is
over there you got an advection diffusion equation, and you got a toolbox of all the possible methods that you employ
Yeah.
over there. Do you have any clue on if there is the perfect recipe that you should employ?
So I did not
Thank
check.
you.
I did not check, but this is a really good point. What's my idea doing this was, okay, we assume that chemistry works. Most people do not assume that numerics work. I mean, some do, but there are more people that are critical of, is this the right numerical method? So I did a very naive computation. So having something that seemingly works and just change the chemistry description. But yeah, sure. I think the numerics might have something to do, especially here. What could be interesting is that in the detailed kinetics, you have more species that are very stiff. And yeah, maybe this needs to be done with some grid refinements. So you can see that the green is actually fine from a combustion point of view, but this is where those spikes come from. Is because it's a very complex problem, because you have a Lagrangian particle. in a Eurasian box that evaporates. So you want it to be fine enough to capture the combustion, but if it's too small, the gradients will go through the roof and the evaporation in one cell will also go through the roof. So this is actually a complicated game. But here we have the same problem in both cases. But yeah, the numerics, especially when you deal with Euler-Lagrange formulation, it's very complicated. Thanks.
Okay. Thank you very much.
That's it.